Okay, so today we are going to start talking about graphs. We are going to spend quite a lot of time understanding the basic definitions and terminology associated with graphs, see some examples, and then if time permits, we are going to do the graph abstract data type, right? Or I think we will be able to do the graph abstract data type today. So question is, what is a graph? So pictorially, this is what a graph is, and what are the terms we are going to have. So graph is always represented by a two tuple, V and E typically. V is what we'll call the set of vertices, okay, and E we'll call the set of edges, right. So set of vertices and a set of edges together specify a graph. So in this picture, these red circles are the vertices, right. I have given each of these vertices a name A, B, C, D, E to distinguish them, and the blue lines are the edges. So an edge really is a pair of vertices. An edge is a pair of vertices, or an edge is specified by giving a pair of vertices. So this edge is set to connect vertices U and V, or we will not use the term connect, but this edge is an edge between U and V. When I say E is equals UV is an edge, then that means that it's an edge between vertices U and vertex V, vertices U and V. So for instance, in this example could be specified, this graph could be specified either by giving this drawing or giving this detail, as in V, the set of vertices is 5 vertices A, B, C, D, E, and what are the edges I have? So each edge, as you can see, is a pair of vertices, an unordered pair of vertices here, right. A comma B is the same as B comma A. All that specifies is it's an edge between vertices A and B. Okay, so A comma B, A comma C is this edge, A comma D is this edge, B comma E is this, C comma D is that, C comma E is this, and D comma E is this. So there are 1, 2, 3, 4, 5, 6, 7 edges, and there are the 7 pairs mentioned here. Yeah, clear? So a set of vertices and a set of edges. So what are they used for? Lots and lots of applications, right? You can model circuits as graphs, right? Each of the component of your circuit could be a vertex, right? So this could be a vertex, 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 this is a vertex, which is your CS201. You are trying to find the path of least resistance to get to CS201, right? They can be used to model networks. So I can take the map of the city, right, and every intersection could be modeled as a vertex, and the roads which are connecting two intersections, right, could be modeled as an edge, right, and then that could be a graph, and I could then start asking questions on various questions on whether how can I go from this place to this place by asking the corresponding question on a graph. So transportation networks, lots of these communication networks, all of them are modeled as graphs. Okay. One more example. So this is a typical student day, right? So you wake up, you meditate first about 201, then you eat, maybe you work, then more CS201, play, CS201 programming, sleep, then you dream of CS201. This cycles, right? Huh? Pardon? There's no room for any other course, is there? No. This is the day before the minor. Okay, so this is slightly different from the graph that I had shown in the previous example. Why? Directed, right? So this is what we'll call a directed graph, right? Because you can't do any meditation before you wake up, right? So there's clearly an edge going from wake up to meditation, right? So every edge has a direction associated with it, right? We'll call such graphs directed graphs. So we'll also consider directed graphs, but in the rest of this lecture I'm going to spend most of the time with undirected graphs. Whatever things I define will carry over in a straightforward way to directed graphs as well. So I'll tell you what the differences are. So to begin with, let me go back to a previous slide. in this example or in this definition, where would the difference be when I am talking of a directed graph? So E comma UV is not just a pair, it is a ordered pair, let us say, right. So the ordering is important. The first vertex would typically specify what the start of the edge is or the origin of the edge, and the other would specify the destination of the edge, where the edge is going from. So what is the start and what's the end? Okay. So as I said, today is a fairly simple lecture. We are going to look at lots of terminology. So for now you've understood what a graph is. So there are two kinds of graphs, a directed graph and an undirected graph. So a graph which is not directed is called an undirected graph, and you understand what a vertex is, what vertices are and what edges are. Adjacent vertices. So two vertices, so this is all terminology associated with an undirected graph now. So two vertices which are connected by an edge are called adjacent, right. So who can tell me, is this vertex and this vertex, these two vertices, are they adjacent? No, they are not connected by an edge, right. Well, this and this are adjacent, this and this are not adjacent either, yeah. So vertices which are connected by an edge are called adjacent. The degree of a vertex, the degree of a vertex is the number of adjacent vertices it has, yeah. So what is the degree of this vertex? 3. So in fact I have written down the degrees of the various vertices on these, right. So this vertex is degree 2, this vertex is degree 3, this is degree 3, this is degree 3. Yeah, everyone understands the degree of a vertex. It's the number of adjacent vertices. Yeah. So sometimes we say that this edge is incident to these two vertices, right. Should I write down the word? So this edge, so if I label this, so let's say this vertex is vertex A and vertex B, and this edge is E. So E equals AB is incident to vertices A and B. Yeah. So this edge is incident to these two vertices. Similarly, this edge is incident to this vertex as well as this vertex. So the degree of a vertex can also be defined as the number of edges which are incident to that vertex, right. So there are 3 edges which are incident to this vertex, so the degree of this vertex is 3, right. These are equivalent ways of saying the same thing. Great. So question, what is the sum of the degrees of all the vertices? जोड़ के देखिए जरा, 3 plus 3 plus 3 plus 2 कितना हुआ? 14. Twice the number of edges. Twice the number of edges. Good. Yeah. Twice the number of edges. Because when I am counting, so let's think of it in the following manner. So the answer is right, twice the number of edges, and the argument is actually half a line of an argument. So pictorially I would say the following. When I am counting 3 for this, I am counting 3 because I am counting this one edge, this edge and this edge. So let me put 3 stones, right, one on each of these 3 edges. Then when I am counting 3 here, I am counting this edge, let me put down 3 stones. Then here I am putting down 2 stones. Here I am putting down 3 stones. Here I am putting down 3 stones. So I have put as many stones or pebbles if you want, as many pebbles as the sum of the degrees of the vertices. Yes? Now if I look at any edge, how many pebbles are there on that edge? Exactly 2. Yeah? So the sum of the degrees of the vertices equals 2 times the number of edges. Great. So that's degree, and you understand what degree is, you understand what an adjacent vertex is, what adjacent vertices are. Now let's define the notion of a path. So a path in a graph is a sequence of vertices, let us say V1, V2, Vk, such that consecutive vertices have an edge between them, right. So, if I take vertex Vi and Vi plus 1, then these two vertices are adjacent, there is an edge between those vertices. So, there are two examples here. So, this is my graph, the same graph as before. Recall that there is an edge between C and E also, right. So, this is a path A, B, E, D, C, E is a path. Why is this a path? Because there is an edge between A and B, there is an edge between B and E, there is an edge between E and D, between D and C, and C and E. So, this is a path. Similarly, this is a path B, E, D, C, because there is an edge between B and E, between D and E, between D and C, right. It is easy to construct examples which are not paths, right. Suppose I had written down ABC, ABC is not a path in this graph. Why? Because while there is an edge from A to B, there is no edge from B to C, right. So, everyone understands what a path is. Any questions so far? Okay. A simple path is a path in which no vertex is repeated, right. So, this is an example of a simple path BEC. These three vertices are all distinct. So, it is a simple path. A cycle is a simple path in which the first and the last vertices are the same, right. So, ACDA is a cycle. ठीक है. DACD is the same cycle, right. CDAC is also the same cycle. So, you can read the cycle anywhere. This is a cycle, this is a simple path. In the previous slide, we had an example of a path which is not simple. This is not a simple path, right. Why? This is not a simple path because vertex E is repeated here. So, in a cycle is a simple path except that the first and the last vertices are the same. That is what a cycle is. Okay. A graph is said to be connected if there is a path between every pair of vertices in the graph. आप कोई भी दो vertices अगर लें तो उनके बीच में अगर path है तो we will say that the graph is connected, right. Okay, is this graph connected? path है, किसी भी दो vertices के बीच में path है. मैं ये नहीं कह रहा हूं कि हर दो vertices के बीच में edge होनी चाहिए. So, इन दोनों vertices के बीच में भी path है. क्या path है? बहुत सारे path हैं. एक ये path है, एक ये path है, और भी कोई path है? बहुत सारे हैं. ये path है, एक ये path है, simple path 4 हैं. ठीक है? So, this graph is connected. This is not connected. There is no path from here to here. ठीक है? So, this is connected, the second one is not connected. And this is a common mistake. Connected में there should be a path between every pair of vertices. If there is a path, then it is connected. If there is no path, it is not connected. Right? So, these two vertices, so again this is a common mistake. When you are writing your minor especially, you are going to say these two vertices are not connected because you do not see an edge between them. That is wrong, wrong terminology. These two vertices do not have an edge between them, but they are connected. They are connected because there is a path between these two vertices. So, we say two vertices are connected if there is a path between them, and a graph is connected if there is a path between every pair of vertices. Is this clear to everyone? Okay. Let us understand the notion of a subgraph. So this is a graph on the left hand side. Suppose I take a subset of the vertices and of the edges such that the resulting thing is also a graph. So I took some vertices from here, this vertex, so this you can see it's corresponding, this I took 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 vertices from here. There are 13 vertices in here, I took 11 of them, and I took some of the edges between these vertices. I have not taken all the edges. As you can see, this edge is not here. Right? This would be called a subgraph of this graph. Okay? Right? I cannot take this edge, right, because the other endpoint of this edge, right, is not there. I have not included it here at all. Right? For an edge, the two vertices between which the edge is running are also called the endpoints of that edge. Right? So this edge, each edge has two endpoints, and those are the two endpoints. So this is called a subgraph of this graph. Clear? Okay. Now let's understand what a connected component is. A connected component is a maximal connected subgraph. So suppose this is a graph, this is one graph, right? This is one graph. It's not three graphs that I've drawn. I've drawn just one graph here. This is not a connected graph. Is this connected? क्या हुआ? This is not a connected graph. Why? Because there is no path from here to here. ये तो मैं दो बार बोल चुका हूं कि ये पूरा एक ही ग्राफ है. ठीक है, ये पूरा एक ग्राफ है एक डब्बे के अंदर. ठीक है, this is not connected because there is no path from here to here, there is no path from here to here. Yeah, so this is not a connected graph. If I look at this subgraph, it is connected. Just this subgraph, these three vertices and these three edges, it is connected. These four vertices and these three edges are also connected. These 5 vertices and the 7 edges on them are also connected. Right? These 3 are the connected components of this graph. Okay. Now, what's the definition of a connected? It's a maximal connected subgraph. What does a maximal connected subgraph mean? Right? Okay. So this needs to be understood more carefully. Right? Suppose I were to take this vertex, and this vertex, right? And I were to take this edge and this edge. This is a subgraph? Yes or no? This is a subgraph of the original graph. But this is not a connected component. I am not going to call this a connected component. Why? Because it's not maximal. So what does maximal mean? So maximal, so when we say maximal in this class, we'll mean a set is called maximal if we cannot increase the size of the set while retaining the property. So a set is said to be maximal with respect to a certain property if we cannot add more elements to the set and retain the property, right? That's not true here. I can add more elements to this set. I can add more edges or I can add more vertices, and both, right? So I can add this edge and it's still connected. I can add this vertex and this edge and it's still connected. I can add this vertex and this edge and it's still connected. I can add this edge, now it's still connected. I can add this edge, now it's still connected. Now, if I add any other vertex or any other edge, suppose I decided to add this vertex, I add this, but it's not connected anymore. Yeah? So this is a maximal connected subgraph. And so we will call this a connected component. So this entire thing is a connected component. This is also a connected component and this is also a connected component. Yeah, इसके अंदर I cannot add any other vertices and still have the property of it being connected. So essentially how, intuitively, how do you think of connected components? You just see which are the pieces which are connected amongst each other. Each of them is a connected component. Okay, as simple as that. Yeah. So this graph has 3 connected components. Okay, more terminology. Forest. Forest. What is a forest? Forest is a jungle. A jungle is a collection of trees and animals, but we'll leave out the animals. So we are thinking of a forest as a collection of trees, right? So these are the trees in the forest. Okay. Now what is a tree here? Okay. A tree here is a connected graph which does not have any cycles in it. Huh? It's the same as the tree that we had till now, except that जो अभी तक जो trees थे उनको हम rooted trees कहते हैं. Rooted trees क्यों कहते हैं? क्योंकि उन सब में notion of एक root होता है. यहाँ पे notion of root कुछ नहीं है. क्योंकि वहाँ notion of root होता है, तो आप जब root से hang कर देते हैं tree को, तो parent child relationships define हो जाती हैं. There is a node, उसके children होते हैं, उसका parent होता है, and so on and on. यहाँ पे we don't have any such notion. ठीक है, तो इसलिए उसको वहां से डिस्टिंग्विश करने के लिए हम इसको फ्री ट्री भी बोल सकते हैं, अदरवाइज ट्री ही बोलेंगे. राइट, इट विल बी क्लियर फ्रॉम द कॉन्टेक्स्ट कि हम एक रूटेड ट्री की बात कर रहे हैं या एक अनरूटेड ट्री की बात कर रहे हैं. सो दिस इज एन एग्जांपल ऑफ अ ट्री. इट इज अ कनेक्टेड सब ग्राफ एज यू कैन सी, एंड इट डज नॉट हैव एनी साइकिल इन इट. This is also a tree, this is also a tree, this is also a tree. When you have a collection of trees, it's a forest. ठीक है? So forest is a collection of trees. Great. So everyone understands this. What are trees? Tree is a connected subgraph which does not have any cycle in it. Okay, more. So I am typically going to use n to denote the number of vertices and m to denote the number of edges in any graph. ठीक है? So what is a complete graph? A complete graph is one in which there is an edge between every pair of vertices. ठीक है? Between every pair of vertices there is an edge. This is an example of a complete graph. This is a graph on 5 vertices. Between every pair of vertices there is an edge. So how many edges does a complete graph have? NC2, right? Because there are NC2 pairs of vertices, and there is an edge between every pair, and so you'll have so many edges. How many edges does a complete directed graph have? 2 times NC2. A directed and a complete, right? So basically there will have to be an edge in both directions, right? So it will become twice. So if a graph is not complete, then the number of edges will going to be strictly less than n choose 2. Right? So in an undirected graph, this is the maximum number of edges that a graph can have, n choose 2. इससे ज़्यादा edges हो ही नहीं सकती. कम से कम कितनी edges हो सकती हैं ग्राफ के अंदर? Suppose I give you a graph on n vertices. 0. It might not have any edge at all. Right? So the minimum number of edges in a graph on n vertices is 0, and the maximum number of edges is n choose 2. Yeah? Okay. So once again we have n number of vertices, m number of edges.
What about minimum in a connected graph?
Yeah, that's the slide. So suppose in a tree, so what is a tree? Recall, a tree is a connected graph which does not have any cycle in it. ठीक है? How many edges are there in a tree? I have said number of edges in the tree is n minus 1. Why?
Every pair of
Huh?
there has to be a path from one node to every. We start from a node and we have to go to every node. And we cannot have a like a cycle. So just starting from a node, you cannot.
So
The 1 to 2, 2 to 3. But we can have path 1, 2, 3 up till n. So number of edges there will be n.
each vertex is degree 2, no? In a tree, every vertex is degree 2, no? ये देखिए, ये इतने आपके trees हैं.
We can count the edges by the edge coming to a node. If we take the notion of direction, so the edge coming to a node is 1. So
What do you mean coming to a node? So is this edge coming into this node or is this edge coming into this node?
Take this as if you're starting from any, if you start from any particular node, you don't have a notion of it. Let the number of nodes be 1 to n. They have to have a path 1 to.
Okay, let's prove this. Okay, घबराने वाली बात नहीं है. It's a true statement. तो इसका proof भी होगा ये एक simple सा, right? So let's prove that. So what will be the proof? So we have to prove that a tree on n vertices has n minus 1 edges. इंडक्शन से करते हैं, as simple as that. ठीक है? So इंडक्शन से, proof by induction. So what should be the base case? Let's say n equals 2. ठीक है? So suppose I have a connected graph on 2 vertices. पहली प्रॉपर्टी है कनेक्टेड होना चाहिए, तो उसमें तो ये एज होनी पड़ेगी, और कोई एज हो ही नहीं सकती ग्राफ में, तो एक एज होगी, तो स्टेटमेंट इज ट्रू. सो नंबर ऑफ एजेस इक्वल्स n माइनस 1 इक्वल्स 1. सो इंडक्शन हाइपोथेसिस क्या होगी हमारी? स्टेटमेंट ट्रू for all n less than or equal to k, let's say. ठीक है? So now the induction step. So we have a graph on, so given a graph on k plus 1 vertices. Why should this have k edges? नहीं, कौन सा एक्स्ट्रा नोड ऐड किया है मुझे तो कोई नहीं पता. आपने मुझे ग्राफ दिया k plus 1 वर्टिसेस का, आप कह रहे हैं इसमें k एजेस है, मैं कैसे प्रूव करूंगा? कोई भी एक नोड हटा दें. हाँ, one leaf, good. Okay, so he's saying something useful. He's saying there is no cycle in the graph. We have to use somewhere the fact that there is no cycle in the graph. आप उसको नहीं यूज करेंगे तो आपने सारे ग्राफ्स में प्रूफ कर दिया कि सब ग्राफ्स जो भी कनेक्टेड है उनमें n माइनस 1 एजेस है, राइट? वो तो ट्रू नहीं है. तो कहीं पे आपको यही फैक्ट यूज करना है कि इस ग्राफ में कोई साइकिल नहीं है. अगर ग्राफ में कोई साइकिल नहीं है तो ही सेज दैट देयर हैज टू बी वन लीफ. ये लीफ क्या चीज होती है? अभी तक तुम गुड. सो लेट्स डिफाइन अ लीफ now as a vertex. A leaf is a vertex of degree 1. ठीक है? So his claim is that this tree, or given a graph on k vertices, given a tree on k vertices, k plus 1 vertices, right? We are given a tree, we are proving this. So the tree, or every tree, has a leaf. क्या करेंगे इस क्लेम का अभी देखेंगे बाद में, बट ये क्लेम ट्रू है कि नहीं? हर एक ट्री में एक लीफ होनी जरूरी है. कैसे प्रूव करेंगे इसको? हाँ, तो इसको प्रूव करने का बहुत आसान सा तरीका है, आपने एक वर्टेक्स लिया, कोई भी एक वर्टेक्स ले लीजिए अपनी ट्री में, उससे एक कोई एज इंसिडेंट होगी, अगर नहीं हुई इससे कोई भी एज इंसिडेंट तो ये कनेक्टेड ही नहीं है किसी से, तो इससे कोई ना कोई एज इंसिडेंट होगी, तो आप इस वर्टेक्स पे चले गए। फिर यहां से अगर ये लीफ नहीं है वर्टेक्स, अगर या तो ये वर्टेक्स लीफ है तो मिल गई लीफ हमें, यही तो हमें प्रूव करना था कि इस ट्री में एक लीफ है, और अगर लीफ नहीं है तो इस पे एक और एज होनी चाहिए। हाँ, अगर लीफ नहीं है ये तो इसकी डिग्री एटलीस्ट 2 होनी चाहिए, तो एक एज तो ये थी जिससे हम आए, और एक एज और कोई होनी चाहिए जिससे हम बाहर जाएंगे। ठीक है, बाहर जाके दूसरी वर्टेक्स पे पहुंच जाएंगे। यहां से एक एज तो ये थी जिससे हम आए, एक एज और होनी चाहिए जिससे हम बाहर जाएंगे, अगर नहीं है तो ये लीफ हो गई, ये वाली वर्टेक्स। तो ऐसे ऐसे हम करते जा सकते हैं, कब तक करते जा सकते हैं? So maybe we come back to one of the vertices we have already visited. अगर ऐसा होता है तो इसका मतलब तो एक साइकिल बन गई, so it is not a tree. तो अगर हम वापस नहीं आते हैं तो फिर हम एक ऐसी वर्टेक्स पे पहुंच जाएंगे जहां से हम आगे जा ही नहीं सकते। ठीक है, तो अगर हम ऐसी वर्टेक्स पे पहुंच जाते हैं जहां से हम कहीं जा ही नहीं सकते तो वो लीफ हो गई, क्योंकि उस पर एक ही एज इंसिडेंट है। तो इसलिए हर एक ट्री में एक लीफ तो होनी जरूरी है। ठीक है, अब इसका क्या करेंगे? एक लीफ तो है, उसका क्या करेंगे? उस लीफ को हम क्लिप कर देते हैं। ठीक है, तो ये वाली जो लीफ है जो हमें मिली, इसको और इससे जो एक एज इंसिडेंट है इसको हटा देते हैं। तो अब हमारे पास क्या बचा? एक ट्री बचा। एक ये ट्री क्यों होगा? ये पूरा का पूरा तो ट्री था, तो ये क्यों ट्री होगा? क्यों कनेक्टेड रहेंगे? बिकॉज दैट वॉज अ लीफ, इसलिए हम कनेक्टेड रहेंगे। ये भी आपको छोटा सा आर्ग्यूमेंट करना पड़ेगा। नहीं, देखिए हम कह रहे हैं कि हमने ये वर्टेक्स और ये एज हटा दिया, बाकी वर्टिसेस पर बिटवीन सो ये जो बाकी वर्टिसेस हैं इनके बीच में अभी भी पाथ है। एग्जैक्टली, दिस एज कैन नॉट बी पार्ट ऑफ एनी सिंपल पाथ बिटवीन एनी टू वर्टिसेस, या बिकॉज अगर आप इस एज को यूज करके कहीं इस वर्टेक्स पर पहुंचे तो फिर आपको वापस इस एज को यूज करके इस वर्टेक्स पे आना पड़ेगा, तो वो तो सिंपल पाथ नहीं रहा, आपने एक एज को रिपीट कर दिया। तो this edge cannot be part of any simple path, and so even after I remove this edge and this vertex, there is a path between every pair of vertices. So this is still connected, right? This is connected, and by removing an edge and a vertex, I cannot create a cycle, right? अगर पहले इसमें साइकिल नहीं थी तो ऐसा नहीं कि एक एज रिमूव करने से मेरी साइकिल बन जाएगी। ठीक है, तो ये अभी भी ट्री है। अगर ये अभी भी ट्री है तो आई कैन अप्लाई माई इंडक्शन हाइपोथेसिस ऑन इट। सो इसके अंदर ये ट्री कितने वर्टिसेस पर है? एक वर्टेक्स हमने हटाया है, वी हैव रिमूव्ड ओनली वन वर्टेक्स। सो दिस इज अ ट्री, सो दिस इज अ ट्री ऑन k vertices and has k minus 1 edges. This is by induction hypothesis. So अगर यहां पे k minus 1 edges हैं और ये वाली एक एज और है, तो इसका मतलब पूरे इस ट्री पे k plus 1 vertices वाला जो ट्री था उसमें k edges थी, and so we proved the theorem. ठीक है, देखिए आपको you have to use the fact, both the facts are critical, that it's a connected graph and it does not have a cycle in it, otherwise you will not be able to argue, right, that it has k minus 1 edges. अगर ग्राफ कनेक्टेड नहीं है तो उसमें तो 0 एजेस हो सकती हैं, और अगर उसमें साइकिल परमिट करते हैं आप तो कितनी एजेस हो सकती हैं? अप टू k choose 2 एजेस हो सकती हैं। तो k minus 1 तभी होंगी जब दोनों प्रॉपर्टीज हैं, कनेक्टेड भी है और साइकिल नहीं है। Okay, so that's the proof for this. Yeah, everyone follows this? most textbooks would have this proof also, so you can also go back and look at one of the texts. So, if the number of edges is less than n minus 1 in a graph, then the graph cannot be connected at all. Why? This statement, if the number of edges is less than n minus 1, then the graph is not connected. Right, so proof by contradiction. Okay, so suppose it is connected. If it is connected, then okay, so let's follow this argument, right? So suppose it is connected. If it is connected, then why is it not a tree? It's not a tree because it has a cycle. So let's remove an edge from the cycle. देखिए अगर आप एक साइकिल में से कोई एज रिमूव करते हैं तो उससे ग्राफ डिस्कनेक्ट नहीं हो सकता कभी. क्यों? Oops, I should have switched, but okay. So what are we trying to argue? If number of edges is less than n minus 1, then G is not connected, right? So this is another useful thing to remember, that suppose I have a cycle.
So G here will take as a graph, not a tree.
G is a graph, right? So suppose I have a graph in which there is a cycle. बड़ा सा ग्राफ है, एक यहाँ पे एक साइकिल है. अब मैं इसमें से एक एज को हटा देता हूं. अगर पहले ये ग्राफ कनेक्टेड था तो अभी भी ये कनेक्टेड होगा. क्यों? आप कहेंगे ये एज हटा दी, कोई ना कोई दो वर्टिसेस के बीच का पाथ खत्म हो गया. किन दो वर्टिसेस के बीच का पाथ खत्म हो गया? मे बी एक वर्टेक्स यहां है और एक और वर्टेक्स आपकी यहां है. इनके बीच का पाथ जो है खत्म हो गया, मतलब वो पाथ इस एज को यूज कर रहा था. अगर वो इस एज को यूज कर रहा था तो अब वो ऐसे जाके और फिर अब ऐसे जा सकता है. हाँ, इस एज को हम इस पूरे से रिप्लेस कर सकते हैं तो पाथ अभी भी रहेगा. सिंपल नहीं होगा पर पाथ तो रहेगा. पाथ होगा तो कनेक्टेड रहा. ठीक है, तो अगर आपके पास कोई साइकिल है, if you have a cycle and if you remove any edge from the cycle, then you cannot make the graph disconnected by doing that. So what is the argument that to prove this claim? If suppose I have a graph on less than n minus 1 on less than n minus 1 edges which is connected, why is it not a tree? It's not a tree because there is a cycle in it. Let me remove an edge from the cycle. I have only reduced the number of edges and it's still connected. Right? If there is another cycle, let me still remove another edge. So I'll only get less than n minus 1 edges and the graph will remain connected. Right? Eventually I'll get a tree after removing all of this. So I am contradicting the earlier claim which says that any tree has to have exactly n minus 1 edges in it. It cannot have less than n minus 1 edges. Right? So any graph which has less than n minus 1 edges cannot be connected. समझ में आ रहा है नहीं? Is there something that's not clear? Right? So a couple of examples. N equals 5, M equals 4. This is a tree on 5 vertices. It has to have 4 edges. This is a tree. This is a graph on 5 vertices and 3 edges. And it cannot be a tree. It cannot be a connected graph at all. Okay? Okay. So let me ask you a question. Suppose I have a graph on n vertices and it has n minus k edges. N minus k edges. How many connected components do you think it has? How many connected components do you think it has? I have a graph on n vertices and n minus k edges. How many connected components it has? K or more? K or more? Okay. Right. K when there would be no cycle, and if there were cycles, then it could even have more number of connected components. Okay, try to prove this. It's a very simple exercise. So you are given a graph on n vertices and n minus k edges. How many connected components does it have? Okay, so more terms. Spanning tree. A spanning tree is a subgraph, which means you are given a graph, so it's a subgraph of a graph, and this subgraph has to be a tree, and it should include all the vertices of the graph, right? So spanning tree में दो words हैं, tree, which means the subgraph has to be a tree, and दूसरा word है spanning. Spanning मतलब it should include everything. Include everything here means include all the vertices. So as you can see, this subgraph includes all the whatever 4, 3, 7 and 3, 10, 13 vertices that are there, and it's a tree. There is no cycle here. So this is a spanning tree of this graph. This is the graph and this is the spanning tree of this graph. G has to be connected. If G is not connected, then there is no notion of a spanning tree, right? If G is not connected, then no subgraph of the graph of G can be a tree, or cannot be a spanning tree, sorry. बहुत सारे टर्म्स हो रहे हैं, हाँ, तो थोड़ा जल्दी जाना चाहिए. So this is a useful thing to have. You know, quite often your network would just be a spanning tree. Suppose these are points that I want to connect, right? So see, these are cities and these are possible roads that I can build, but I just want to put the minimum amount of effort. I want to build as few roads as possible, so that all these cities are still connected. So I could build a spanning tree. Yeah, but this does not provide you any fault tolerance. What does that mean? अगर एक भी road जो है बंद हो गई तो disconnect हो जाएगा. You cannot reach from some city to some other city then. Right? As you can see, if I cut off this link, then these 4 vertices would be disconnected from the other 9 vertices. ये अगर बंद हो जाती है, ये road अगर मैं कट कर देता हूँ, तो these 6 vertices would be disconnected from the other 7. Right? So spanning trees are useful, but they don't provide much fault tolerance. Okay, bridges. Let's talk about bridges now. Königsberg, right? This is a city in Germany or Austria, I don't remember where. Okay, so Pregel River. Okay, I don't remember where this is. Well, this city has this nice thing. This is there is a river flowing through the city, and there is an island in the river, and there are bridges in this manner. So A is this island, and there is a bridge from here to here. So there are 7 bridges in all, right? These black bars are the bridges. So the question is, can you start from here, let's say, or any point? So can one walk across each bridge exactly once and return to the starting point? Why no? So suppose I start from here, I can take this bridge, go here.
You can go on land also.
हाँ, you can go on land, of course. ठीक है, आप यहाँ से यहाँ पहुँचे, फिर आप यहाँ से यहाँ आ गए, राइट? फिर आप अगर यहाँ से यहाँ चले जाते हैं, तो आप वापस यहाँ आने के लिए इस पॉइंट पर आपको एक और ब्रिज चाहिए, पर ब्रिज तो आप दोबारा नहीं आ सकते, तो आपको यहाँ से यहाँ गए, यहाँ से यहाँ गए, so on and on. Let's see whether we can solve this problem or not. So suppose, you know, this would have been useful if you were a postman who had to visit the various bridges, right, and you did not want to retrace your steps. So this is also known as Euler's problem, and Euler proved that this is not possible, and we'll give a simple proof for that fact. right? So we can model this thing as a graph. Yeah. So there is this island A. So these are going to be the vertices of my graph. This island A, this is one piece of land. Then there is this part B, right? Because I can go from anywhere to here. This is one vertex. There is a vertex D and there is a vertex C, which is this part. So I will have a graph with 4 vertices in it, A, B, C, D, right? And then depending upon, so since there is a bridge from B to A, in fact there are 2 bridges from B to A, yeah. So I will put 2 edges between B and A. Similarly, there are 2 bridges between A and C, so I will put 2 edges between A and C. There is one bridge from A to D, so I will put one edge between A and D. There is a bridge between D and B, so I will put one edge between B and D and an edge between C and D. So I will get, this is not a graph. Why is this not a graph? Because we did not define a notion of 2 edges between a pair of vertices, right? We just talked of a pair of vertices, right? The edges don't form a set, they form a multi-set. So this is called a multi-graph. What's a multi-graph? In which there could be many edges between a pair of vertices. That's called a multi-graph. But this captures that problem in a certain sense. So what is, so an Eulerian Tor is a path that traverses every edge exactly once and returns to the first vertex. That's exactly what we want to do, right? Because these are the bridges, so we want to traverse each bridge exactly once and return to the starting vertex. Can you do that on this graph? So the same problem can now be thought of here. Can I start from A and come back to A and visit each or traverse each edge exactly once? So the same question is saying, can you draw this picture without lifting your pencil? Yeah? Without lifting your pencil or redrawing an edge, you know, coming back over a line twice. हाँ? So नहीं कर सकते. क्यों नहीं कर सकते? इसका बड़ा simple सा reason है. So Euler theorem says that you can do this if and only if every vertex has even degree. क्यों? क्योंकि आप, when you come to a vertex, you come by one edge and then you have to go by another edge, and if you come again, then you will need another edge to, a fresh edge to go off by. So every vertex has to have an even degree for this to work. But here there are 2 vertices with odd degrees, or 3 vertices with odd degrees. Oh, sorry, all vertices have odd degrees, right? So clearly this cannot be done. Yeah? Okay, so now let's quickly do the uninteresting part, the abstract data type. So, so the graph can be thought of as a container of positions. So you have the regular methods, right, for any positional container like queues and stacks. We always had these methods called size and isEmpty, and elements would return all the vertices and the edges, let's say, right? And you can have some methods like swap, which can swap 2 positions, replace element, those kind of things. These are methods associated with the regular positional container. Swap is a generic method for any positional container, right? When you are saying that provide 2 positions and swap the contents at those 2 positions. That's the swap method. Right. So here I am not saying it specifically to the graph abstract data type, right? You will have to think of what it would mean. So you could decide on what it means here for this particular data type. But I am saying it's a generic method. These are all generic methods for positional containers, and I am just saying it in that context. Right. So here I have the methods which are specific to graphs. So num vertices could be a method which returns the number of vertices, num edges, number of edges. Vertices would now be an enumeration of all the vertices, right? So it would be a method which returns a iterator, right, which will let you iterate through the various vertices in the graph. Edges could be a method which returns all the edges. Okay, Directed edges would be a method if you had a directed graph, it would return all the, enumerate all the directed edges in the graph. No, what does enumerator do? An iterator, it basically returns an object which has two methods associated with it. One method is next and the other method is whether there is anything left, has next, whether there is a next method, next element at all or not, right. So, as every time you call next, it gives you a next object in the enumeration, right. So, when you are enumerating edges, I call next once, it will give me one edge. When I call next again, it will give me another edge. What order these edges come in, that you typically do not know, right. It depends upon how you have implemented the iterator. Undirected edges could similarly enumerate all the undirected edges. Incident edges, if I specify a vertex, it would enumerate all the edges incident at that vertex, right. Okay. So, this is for an undirected graph, incident edges. For a directed graph, right, there are two kinds of edges. Either there would be edges which start from this vertex or there would be edges which end at this vertex. So, you could have a notion of in-incident edges, which are edges entering the vertex V, which are ending at vertex V, and you could have an out incident edges, which are edges which are starting from vertex V, going out of vertex V. Opposite, so I specify an edge E, right, all of these are objects, an edge is also an object, and I specify one endpoint of the edge. So, this method gives me the other endpoint of that edge. Degree gives me the degree of a vertex. In degree, so degree would be for an undirected graph. For a directed graph, there would be the notion of an in degree and an out degree. In degree would be the number of edges coming into the vertex, out degree would be the number of edges leaving the vertex. Similarly, I could have adjacent vertices. Adjacent vertices would be a method which returns an iterator over all the vertices which are adjacent to this particular vertex. This would be for an undirected graph. For a directed graph, you could similarly have a notion of in adjacent and an out adjacent vertices. Yeah. Then you could have a method R adjacent, whether vertices, two vertices V and W are adjacent or not, right. So, this would be return a Boolean value. End vertices, given an edge, it will return the two endpoints of that edge. Origin, for a directed edge E, it would return where the edge is starting from. Destination, for a directed edge E, it would return where the edge E is ending. Given an edge E, it will tell whether it is directed or not, right. This method would be useful when you have what are called mixed graphs. Mixed graphs, some edges are directed and some are undirected. Can you give me a setting where it would be useful to have a mixed graph? What kind of a problem setting can you imagine where it would be natural to have? Yeah? Roads, a traffic network once again, where you have some roads are one ways, right. So, your bidirected edges, roads which are two way could be undirected edges, and roads which are only one way could be directed edges, right. So, there such a method would be useful, because given an edge you can then determine whether it is a directed edge or an undirected edge. Okay. I'll just take, I guess this is the last slide, yet yes it is. So, make undirected E. So, you are given an edge E and you set it to be an undirected edge. You can have a method which reverses the direction. So, these are, you can have tons and tons of update methods also, right. You can have methods to create the graph, change, remove an edge, remove a vertex, do whatever you want, right. So, set direction from, so you can set the direction of an edge suitably. You just look through this, these slides are available, right. So, this is just a subset of methods. Depending upon what application you have, you could design your own set of methods, right. So, the graph can be thought of as a data type, is an abstract data type on which you can have a bunch of methods which you can use to update and modify the data type. So, with that we will end our discussion on graphs. We will continue it in the next class, however, to see how to actually represent a graph. What kind of data structures can you use to represent graphs.